Greetings. Today on this episode of MatHAMMatics, we will be exploring Pythagorean theorem triples and special right triangles. Enjoy. So to begin thinking about the Pythagorean theorem, it would be helpful to quickly remember what it is that we are talking about. Ultimately, when you have a right triangle and you have two legs and a hypotenuse, call one leg A, one leg B, and we'll call the hypotenuse C, we know that the Pythagorean theorem states that leg squared plus leg squared is equal to hypotenuse squared. Actually, I have a nice little Lego illustration of this. Here you can see that we've got one leg of our right triangle represented by 3 pegs, one represented by 4 pegs, and the hypotenuse here nicely is represented by 5 pegs. And what this theorem states is that if you take that leg and square it, right, so notice we've got the 3 squared, and we've got the 4 squared, and we have this 5 side squared. Do these things in fact equal one another? So let's find out. And so we can see here very nicely that 3 squared plus 4 squared does in fact equal 5 squared. And what's really nice about this is that A, B, and C, right, both legs and the hypotenuse are integers. And those are just a lot nicer to deal with than other types of numbers, right? And so it kind of makes you wonder, are there other situations where the legs and the hypotenuse would all fall to be integers? And the answer, of course, is yes. These are our Pythagorean triples. So there are an infinite number of Pythagorean triples, right? Leg and hypotenuse combinations that fall into this pattern where all 3 are integers. But there are 4 that are really commonly used. These are just nice to kind of have as in the back of your mind, make some of these Pythagorean type problems or even some of our trig problems a little bit simpler. The first one we just explored, that's the 3, 4, 5 Pythagorean triple, right? That if your legs are in a 3-to-4 ratio with a hypotenuse of 5, then you will be in Pythagorean triple land, right? You'll have a right triangle. 5 to 12 to 13 is another one of these Pythagorean triples. 7 to 24 to 25 is the third, and 8, 15, 17 is the fourth. These are the most common, not all of them, right? But these are the most common Pythagorean triples. And the one thing that we want to make sure we're also looking out for when we look at these triples is we want to think about scale factor, right? Spelling is helpful. Okay, think about scale factor with these, right? We could very easily take these ratios and apply a scale factor. A 6, 8, 10 right triangle will also nicely fall into this Pythagorean triple combination, right? A 10, 24, 26, right? So on and so forth. So the scale factor can apply to these Pythagorean triples just as nicely. Okay, so just a nice little thing to have in our back pocket as we begin to look at right triangles. Now moving on, the bulk of what we want to discuss today is this idea of a special right triangle. And special right triangles are really fun. Really fun because they can help us with some of our trig applications, and it's a building block, a fundamental skill in leading us towards circle trigonometry, right, which is down the road for us. there are two special right triangles that we're going to talk about today, right? And there really are two to worry about. The first right triangle is an isosceles right triangle, okay? One of the things that we know about isosceles right triangles, of course, if these two sides are the same, that also means that the base angles of the right triangle will be the same. And since it's a right triangle, we also know that these base angles are going to measure 45 degrees, right? Because 45 degrees plus 45 degrees plus 90 degrees would give us the 180 degrees in a triangle, okay? This type of triangle is often called the 45, 45, 90 special right triangle, indicating its three angle measures. Well, what is so unique about these angle measures? Well, let's take a look at the relationship of the tangent. So let's call this triangle, we'll give it a name, let's call this A, B, C for a minute. And let's figure out what is the tangent of angle A, right? So let's just say that, and we know angle A is 45 degrees. Well, let's go to our calculator and find out what is the tangent of 45 degrees. Make our calculation, and we can find, right, and you should be able to find this on your calculators too, that the tangent of 45 degrees comes out nicely to be 1. Well, why is that so important, right? What is the use there? Well, we know that the tangent is an opposite over adjacent relationship, right? So if we're talking about angle A here, we're talking about this side over this side is equal to 1. Well, why is that useful? Well, what that tells us is that these two side lengths are going to be in a 1-to-1 ratio. Do we need to go through this whole process to get there? Not really, right? If we had just thought about the congruence nature of these two sides, we know these two sides have to be the same, right? And so the sides in a 45, 45, 90 right triangle are in a 1-to-1 ratio. And even more uniquely now, because these are in a 1-to-1 ratio, we can really simply figure out what the ratio of the hypotenuse would be. Go back to our Pythagorean theorem, right? We've got side squared plus side squared is going to equal hypotenuse squared, right? Well, 1 squared plus 1 squared is 2. And if 2 is equal to c squared, then we know that the hypotenuse is rad 2. Right? It's going to be a lot easier to leave this in simplest radical form. So in a 45, 45, 90 triangle, our legs are in a 1-to-1 to rad 2 relationship with our hypotenuse. Okay, so that's the 45, 45, 90 triangle. The second of these special right triangles, so again, we'll get ourselves a triangle here. That is not the triangle that I was hoping to draw. Let's see if it's a little bit happier with this one. There we go. All right, so here we have a second type of triangle, and this one I'm going to give angle measures of 30 degrees and 60 degrees. Right, and this is our 30, 60, 90 special right triangle. Okay? So in order to think about these two things, let's take a look at a different trig function to figure out some useful information. Okay? Let's take a look at let's try the sine. Right, again, let's give this a name. Call this D, E, F. And let's just take a look at the sine of angle D. Again, that would be the sine of 30 degrees. And so if we go to our calculator here, and we test out the sine of 30 degrees, we see that we get 0.5 as the value of the ratio. Okay, so the sine of 30 is 0.5. Well, what's maybe a more useful way to think about 0.5? Well, that is, of course, 1/2. And so if the sine of 30 is 1/2, and we know that the sine is the opposite over the hypotenuse, what do we know is true about the ratio of this side here to this side here? Well, of course, it's in a 1:2 ratio. And so now we know the ratio of these two side lengths. We've got the 1:2 is the hypotenuse here. And so how do we figure out what this side is? Well, again, we can utilize the Pythagorean theorem. So we know that 2 squared minus 1 squared will equal a squared, right? This side will equal hypotenuse squared minus this. Well, 2 squared is 4, minus 1 is 1, right? So there's 3 is equal to a squared, or a is equal to the square root of 3. And so here are the ratios for our 30, 60, 90 triangle. 1 to rad 3:2. Again, we're always looking at these ratios as leg to leg to hypotenuse. Leg, leg, hypotenuse. And so as we start to explore some application problems with these, see if we can start to apply these ratios and not have to rely on going to our calculator for the trig function or performing the Pythagorean theorem. Okay. Again, be on the lookout for scaling factors and ways that we can apply that. And hopefully this is really helpful. And if you have any questions, please reach out. Have a good day.